Okay, so we were looking at unusual chromosome structures in the last lecture segment, and I forgot to show you the picture of the fragile site on the X chromosome. You can see these are, of course, sister chromatids, so you can see right here the narrowing of the chromosome. It's the result of the expanded trinucleotide ZGG repeating sequence. And so the chromosome will tend to break right at that location there. All right, but now we're going to move on to, instead of unusual chromosome structures, we're going to look at unusual numbers of chromosomes. And in this lecture segment, we're going to look at aneuploidies specifically. And then in the lecture segment after this one, we'll look at polyploidies. So the variation in chromosome number overview is that you have this term called euploidy, which you may never have heard before. But euploidy, U means true, and ploidy means sets, or set. And so euploidy would be the condition of having complete balanced sets of chromosomes. So like monoploidy is a type of euploidy because you have one full set of chromosomes. Diploidy, 2 full sets. Triploidy, 3 full sets. Tetraploidy, 4 full sets. As long as you have full, complete, balanced sets of chromosomes, then that's a euploidy. And just as a side note, we will talk about polyploidy. It's possible in some animals, not in human though, and in some pretty common actually in plants. So if euploidy means complete balanced sets of chromosomes, then aneuploidy refers to not complete balanced sets of chromosomes. Specifically, it's the case where a cell has either an extra chromosome of a certain type or is missing a chromosome of a certain type. But it sets the whole set of chromosomes out of balance. So in these cases, you would use the term nullisomy, meaning no copies of a chromosome of a certain type. Monosomy, only one copy. Disomy, 2 copies. Trisomy, 3 copies. And tetrasomy, 4 copies. Usually we don't go beyond that. We don't need to go beyond that because we don't commonly see things in addition anything other than these. Now, how aneuploidy is created is through an event called nondisjunction. Nondisjunction typically is going to happen in meiosis, although we'll also look at how it can happen in mitosis. But in meiosis, nondisjunction is an error in which either homologs or sister chromatids are not segregated correctly. So we're specifically talking about nondisjunction at anaphase 1, for example, would be where sister chromatids are not correctly segregated. Normally, if you have a pair of homologous chromosomes, one of the pair should end up in this daughter cell and the other one should end up in this daughter cell. This daughter cell here is not empty, it just doesn't have any of the red type of chromosomes. So let's assume all the other types of chromosomes are segregating correctly. Then what we're saying is that this chromosome at the bottom doesn't have, it has all the other ones, but it's missing a copy of the red chromosome. This cell got 2 copies of the red. And so let's assume that meiosis 2 happens normally, then this cell, these gametes will have 2 copies of the red chromosome. These 2 cells will have no copies of the red chromosome. And when that gets fertilized by a normal gamete that has 1 copy of that type of chromosome, then you'll either get zygotes that are trisomic, they have 3 copies of that chromosome, and then 2 copies of every other type of chromosome. Or you'll get a cell that's monosomic for this chromosome, only 1 copy of this chromosome, but 2 copies of all the other chromosomes. So that's what you would get in a meiosis 1 nondisjunction. In a meiosis 2 nondisjunction, we would assume that meiosis 1 occurs normally, but in meiosis 2, up here, you see that the second anaphase doesn't segregate the sister chromatids correctly, so that these 2 cells are unusual. And when either of these top 2 cells get fertilized, you can end up with the trisomic or monosomic zygote. However, at the bottom, these 2 cells are normal, so you would get normal zygotes from those. All of us contain some of these unusual gametes. Okay, what we're saying is that not most of the time the chromosomes segregate correctly in meiosis, and most of your gametes have an exact one set of chromosomes. But you will have a couple of cells in your body that will do this nondisjunction, and so you'll have a couple of gametes. Among the thousands of normal gametes, you'll have a couple of these abnormal ones. And they can be trisomic, they can have an extra copy or a missing copy of any of the chromosomes. It can be chromosome 1, chromosome 2, any of them can be found in people's gametes. Now, if you have a nondisjunction in mitosis, that would be where the chromatids are not correctly segregated at the metaphase and anaphase stage. Then you could get somatic cells that have the wrong number of chromosomes. And then as that cell continues to divide, you'll get a group of cells that have the wrong number of chromosomes. The effect of nondisjunction mitosis really depends on what kind of cell goes through this nondisjunction. If a skin cell goes through nondisjunction, the cell may just die if it has too many chromosomes or too few. But if you have a nondisjunction in like the zygote or in the early embryo, then you can get all of or part of the embryonic cells having this problem, and that could be more serious. In humans, one of the most common trisomies, other than the ones we talked about that affect the sex chromosomes, from chapter 4 we talked about Klinefelter syndrome, which is a trisomy of the sex chromosomes. But among the autosomes, you have a couple of trisomies that are viable in human. Viable means can survive embryonic development through live birth. So Down syndrome is one of those. It has a designation of 47, plus 21. That means 47 chromosomes in a somatic cell. And the extra chromosome is chromosome 21. The individual with Down syndrome has a certain facial appearance, and they have a retarded mental and physical development. Their life expectancy is typically less than 50 years due to some of the symptoms that come from this: respiratory disease, heart malformations, leukemia, and Alzheimer's. But 50 years is a pretty good prognosis, considering that almost all of the trisomies of the other autosomes are fatal. So this is one of the few trisomies of the autosomes that's really pretty survivable. It doesn't mean that some embryos won't be aborted that have a trisomy 21. It just means that some make it. We know that trisomy 21 is the result of nondisjunction almost always in the egg, in the formation of the egg. And the older the mother is, the more chance she has of having one of these unusual eggs. If you perform an amniocentesis to get cells from the embryo and then karyotype those cells, you can diagnose a Down syndrome baby before the birth. Now, some other human trisomies that are viable are one's called Patau Syndrome. That involves an extra copy of chromosome 13, and Edwards syndrome. This shouldn't have an S on it. Edwards syndrome, which has an extra copy of chromosome 18. But these, even though they survive to live birth, they usually die early in the first year of life. So this is a karyotype of an individual with a trisomy of 21. Here's the 3 copies of 21 here. And this would be a boy because they have an X and a Y. So it's pretty easy to see on a karyotype. These are just some pictures that I took from Google Image of individuals with Down syndrome. And it doesn't matter what race the children or what race the individuals are. You can still see a certain phenotype in the eyes, sort of a somewhat flattened face in a way. It's just a characteristic appearance. Not all of these have a characteristic appearance, but Down syndrome definitely does. Now, Patau syndrome, one of the giveaway phenotypes is the cleft palate combined with the extra fingers, polydactyly. Those are the external features. Internally, there are a lot of abnormal formations in the organs, so that's the main problem. These things can be fixed to some extent, but it's the internal organ malformations that create lethality before the first birthday. Edwards syndrome, not as much obvious external problem. They do have this funny clenched hands that I think is kind of funny, but that's not going to be what kills them. It's going to be congenital heart disease, kidney abnormalities, and other kinds of microcephaly and polycystic kidney, horseshoe kidney. These kidney problems, the heart problems, that's gonna cause lethality. Now, I have seen there is a support group for the trisomy 13 and trisomy 18 individuals, because there are a few individuals who don't die in the first year, and those families really don't know what to do because the medical community isn't really used to seeing that. So I saw a support group. I was at a conference for medical genetics, and there was a support group set up for people who have children who survived the first year that have a Patau or an Edwards syndrome. So I thought that was interesting. I did talk to the families that were there just because I was interested, but most of the time the individuals won't make it past the first year. Now, there is a case or an existence of what's called a familial form of Down syndrome. Most Down syndrome is just a random mistake during meiosis that gets an egg with an extra copy of 21. And everybody has a certain risk of that happening during the formation of their eggs. Or in the formation of sperm, 5% of those. But a familial Down syndrome would be caused by a fusion between chromosome 14 or 15, I wrote 15 here, but it can be 14 or 15 with chromosome 21. I think it can even be chromosome 13, but 14 or 15 are pretty common with a chromosome 21. I don't know if you can see it here, but this copy of 14 on the right side has an extra piece. That's actually chromosome 21 that has inverted and fused to chromosome 14. So the inversion and fusion of two chromosomes is called a Robertsonian translocation. And what that creates is a familial form of Down syndrome, because not just in one generation, but in multiple generations of the same family, you'll have a high risk of having a child with Down syndrome. So this picture shows basically how this works. Normal parents are supposed to have a copy of 21, 2 copies of 21, and 2 copies of 14 or 15. And so the gametes should get 1 copy of 21 and 1 copy of 14 and 15. Person who has this translocation, this fusion chromosome, will have 1 copy of 21 here, 1 copy of 21 fused to 1 copy of 14, and then another separate copy of 14. So they have 2 copies of 21 and 2 copies of 14, but these are fused. So during gametogenesis, which is meiosis, you'll get these types of gametes are all possible. So you get these weird gametes. Now, we're not tracking the other chromosomes. All the other chromosomes, autosomes and sex chromosomes, will segregate normally, let's assume. But with respect to chromosome 14 and 21, you'll get these different gametes that have these different possibilities. And so when any of these gametes meets in a fertilization event with a normal gamete, then down here at the bottom you see all the things that you could get. There's a bunch of things over here on the right that would be aborted. A monosomy of 21 will be a spontaneous abortion, a natural miscarriage. A trisomy of 14 will abort, and a monosomy of 14 will abort. So of the things that can survive, what we end up with is 2/3 of the things that can survive will result in normal offspring, phenotypically normal. But 1/3 of the births will result in Down syndrome. That's pretty high risk. 1/3 of your children are at risk for Down syndrome, and that would be familial. And it wouldn't just be in this generation; it would be passed on. Especially this translocation carrier would also be at risk for having children with Down syndrome. So you'll see Down syndrome in multiple generations in a family. That's unusual, and that would cause you to think about some kind of familial case of Down syndrome, like a Robertsonian chromosome case. This is some data showing that mothers who are older, getting close to 50, have a much higher risk of having a child with Down syndrome compared to a mother who's 40 or less. You can see this kind of exponential increase between the ages of 40 and 50 in the risk. And that just is because the risk of having an unusual, probably anaphase 2 nondisjunction is higher as the eggs are older. There's just a higher risk of mistake during meiosis. All right, so we will continue with polyploidy in the next lecture segment.